Hi everybody, welcome to today's session. Having understood the additive attention from our past session, now we are going to see today some different methods using which attention also can be deployed. During the pre-transformer era, there were several different methods was experimented to make attention more effective. We are going to focus on one single research paper which describes us around 6 or 7 different techniques to customize the attention. Although they are working with the pre-transformer technology, they are very good in terms of developing foundation which may help you to customize attention for your own specific purpose. Just a flashback on what we had learned in the Baznow attention. We started with the initial state 0 from the decoder, right? Which means that whenever a first word in the decoder was appearing, we were actually using the previous hidden state, which means if you are on ith time step or y1 time step, then we are using I-1 hidden state to use it as a query and attend the output of the encoder, right? That's first thing you notice. The second thing was that the context were formed by adding up all these weighted hidden states, and then the context vector we were adding in our code in the input. That eventually gave us the hidden state S1 and the final output. That was about our additive attention. Now we are coming to the Luong attention. In this paper, you can see effective approaches to attention-based neural machine translation 2015. In this paper, Luong is going to propose various other techniques, broadly classified into 3 buckets. One is the how it is sequenced. The sequencing pattern was changed, how the query sequencing will be done. We'll just talk about it in a minute. A second change what was proposed was the span of the attention, how much of the encoder output will be considered for creating the attention. And the third part was the scoring mechanism itself, which will change from additive to multiplicative. We are going to discuss this one by one. Now, the first is how the sequencing was changed. See that one. Earlier, we were dependent on I-1 hidden state. Now, without depending on the I-1 hidden state, we are going to feed the first word, input word to the decoder, generate the hidden state, and then that hidden state is used to attend the encoder's output. Which means if we are on ith step, we are also using ith hidden state to attend the encoder output. So that's the first change. As I said, the sequencing pattern is changing. Second change is that span of attention. Now it is window based. Instead of attending the entire output of the encoder, we are now going to attend only a portion of the output, which is a window we can think about. The argument behind this is that if it is a long sequence, then it is very expensive to attend all the output sequence of the encoder, and that may not be relevant. Most relevant will be possibly a neighborhood of the current word. So the current word is the PI, position of the current word at ith time step. Consider that as the middle point, and then you are defining a D hyperparameter, which is the distance from this, which will go towards the top and the bottom or right and left, giving us a window size. And the attention will be done only on that window itself. So this is what is called the local attention. What is to be noticed here that in the local attention you have, or window based attention, there are again 2 different variety which we can think of, A and B. If it is 2, then it is 2A and 2B. The first one is the monotonic alignment, where it is assumed that there is some sort of correspondence between the source and target language word by word. So if we are in the word position 1, it is assumed that the target word 1, also sequence 1, will have higher relevance. So PI is equal to ith step itself. That's the monotonic alignment. And the second way the position can be determined is by a learned prediction of the position, wherein there is no assumption of one-to-one correspondence, but they are thinking that let the system learn from a neural network, which is here. You can see there is a WP. This weight is learned through a neural network, and pass through a sigmoid activation. So because of sigmoid, the range will be between 0 and the T, which is the center decoder output, and then it will give you a position which is in between 0 and T. So that's the learned prediction. The next one is consider the full window, which is earlier what we had learned as Bahdanov attention. It is very similar to that attention mechanism, where all the words were considered. Now this is all about span of attention. So we have covered two broad categories. One is the sequencing pattern got changed from I-1 to ith hidden state to be used, right? And second is the local attention versus global attention. And within local we have two varieties. There is one more change, which is once the context is formed, in our code we are not going to add it to y1, the input vector, but this is going to be added with the hidden state vector. Then it is going to be fed into the final dense layer, which will give me the output. Rest of the thing will remain same. Now let's move to the scoring mechanism. You would recall that the first step was to broadcast this query or the decoder representation of the word or repeat them up to the T step. Then they were passed through a dense layer. So there is a learning happening. Query was transformed from this word representation vector to some other representation which is called the query. So it's a dense layer, one neural network was here. Similarly, at the encoder side, all the encoder output were again passed through a dense layer, a neural network, converting them as a key. So key and value is not same. Keys are the learned representation of the values, right? Then they were added together. So one network, two network, then they were added to create k plus q, which is why it is called the additive attention. And then finally they were passed through another neural network having a single neuron, if you recollect, to convert it as a scalar number, which is the score. To get to the score, we essentially used 1, 2, 3 neural network and one additive operation. Now let's come to the multiplicative attention scoring mechanism proposed by Luong. In this, you see this portion, which is the broadcast to T dimension, remains same as is. Then the query is taken as is. I mean, directly the queries are coming to us as a entity which can be readily used without getting it passed through a dense layer. So we reduced one neural network layer here. Similarly, for the values part also, you see it is directly available for us as the key. Neural network is also removed here. So going forward, many places you will read paper where you will see that the key and values are the same. But in additive attention, in our previous video, we learned the values are transformed into key through a neural network. So value and key is not same there. Here, value and key is same. So both variety exists. So okay, so that is the second change in the scoring mechanism we are seeing. Now what is happening is that we take any word from this broadcasted array. It is all same because all of them at one time step are nothing but a repeat of the same vector. It's query. Similarly, we take one word from the encoder output. Word means the hidden state of the word. So let's say that is a HJ, and if we do a dot product between them, we get the similarity score of the word. You can see the power of the dot product, right? If you want to have a quick recap of how this dot product helps getting a similarity score between two words, refer to my previous video. It's a very basic video on basic course, rather, understanding vector and the dot product and the other way of measuring the similarities, which is distance measurement. So you can just have a quick refresher on how this dot product helps. So here we are seeing the power of dot product. What essentially it is doing is that it's removing 3 number of neural network directly using the representation vector of the words of both source and target, measuring them by their similarity score, and we are getting this score. Fine. So this is what is multiplicative attention, and more you will see that this is used more frequently than the other one, additive one. Now this is a product with a single word, but we have to do this dot product for one particular time step. Let's say 1, y1, hidden representation is s1. So for s1, I have to do this dot product for all the words h1 to ht. Therefore, you can think of h1 to ht as one set of values, and then si is repeated those many times, t number of times. Therefore, together they are forming a matrix. So we can do this dot product operation parallelly by performing a matrix multiplication k cross q, and that is why again it is termed as the multiplicative attention nature. Okay. Rest of the stuff remains same. Attention score is again a function of si and aj, as we have discussed that it is not si minus 1 anymore, it is the current step, and then this is the function which is nothing but a dot product. Rest of the things remain same, calculate the context vector and so on and so forth. We also discussed about the predictive alignment, right? In the previous slide we discussed that the position can be monotonic or it can be predictive. So when it is monotonic, this weighting mechanism or this scoring mechanism will work. But when it is predictive, we want to ensure that this prediction, this position is actually in the middle of the window, which means that middle of the window gets the maximum score. In case of monotonic alignment, we are seeing that the maximum score should be focused on the current word, which is if I am at y1 step and if decoder also has a y1 value for this, so they have a strong relationship. That was the assumption. Here the assumption is that the prediction has to be somewhere in the middle, and then as they drift from d distance right and left, it should rapidly fall down, creating a bell-shaped curve. So to impose that condition, we are giving this Gaussian formula. This formula may look like terrible, like the way the Gaussian standard formula works. So you see, this is the standard Gaussian normal distribution, where there is the exponential term, x is the entire range of values, and then mu is the mean position, and then sigma is the variance. And as you can see, so this is the term which actually determines the shape of the curve, which will be that in the mu position it will be maximum probability, and as you move away from the mu up to the standard deviation or up to the variance, which is 2 sigma square, it will rapidly fall. This particular term, which is 1 by square root of 2 pi sigma square, is nothing but a normalization term, which makes it standard Gaussian normal distribution, where the variance ranges from 0 to 1. Now look at our formula that we had used there, or Luong, what he has used to make the attention score distribution in a Gaussian manner. You can see that they have replaced this x by the t number of time step, all the data point which is coming out from the encoder, and pi is the value or the mean we are interested in, where maximum weight should be given, and sigma is actually nothing but the distance from the mu position, and we know that that is the d is our hyperparameter. We define that how large is the window size we want to take. So that's how this formula gives the attention score a bell curve like shape. It may not be exactly show such a nice bell curve, but nevertheless it will follow these characteristics where the maximum weightage will be at the current pi position. Mu will be pi. Okay, so that's all about the Gaussian distribution. Now let's go to one more variety of the multiplicative attention. Earlier we said that the keys is equal to value, but Luong also proposed another variant where he said that the let key be learned through a dense layer. So value is not equal to key here. That's the only change he has proposed. Rest all of the stuff remains same. One where value is equal to keys and simply doing a dot product. Another where the keys are learned through a dense layer, then doing the dot product. This may be helpful when you have a shape which is not exactly equal to query. So it may help you to learn some additional information, also help to match the size of these two vectors. Luong also have the proposal for concat, which is a concat based scoring, little bit similar to what we have already learned through Badnau additive attention. Before coming to the code, I just want to show you that in the Tensorflow tutorial, translate text with sequence model, this attention layer was also built. They have also started with similar approach, that instead of going directly to the current state of the art transformer models, they are making us aware of how attention actually works. So the essence of the tutorial is to develop some sense of how attention works. Unfortunately, when they were building the cross attention here, they are using a layer which is keras layer, multi-head attention. You are not getting real intuition what is exactly happening inside this multi-head attention. So the attention mechanism itself they have not explained properly here. On top of that, they are jumping a couple of steps ahead and going directly to multi-head, which will be a subject we will learn in detail later, right? So that's the reason we are taking trouble to develop our own code and developing the intuition, attention mechanism and customization. So this will possibly help developing your own customization or customized model in future. Okay. In the code, what to be noted here is that we have imported this dot function from the keras layer, Tensorflow.keras.layer, along with all other thing whatever we had done before. We have also imported dot. I have added little bit more data. I think earlier it was 20,000 or 30,000. With that data I had done, and because of the 4-5 additional neural network, the training took longer time. But now it is simplified. We are going to do only the dot product based attention. As you have seen, that's very simplified now. For scoring, we don't need any neural network. Just doing the dot product between two vector, right? To vector representation of the word. So I utilize this opportunity to increase the number of example little bit to 40,000. That's the second change which I have done. Now this is the place where we are developing the attention layer. You will appreciate that in this there is no neural network, unlike in Bazlao attention where we had this 3 neural network defined in this stage. The call function still accepts query and values as before, but look at this, the query with time access is expanded. We said that it will be as is, there's no change. You have to expand it by the t number of time step or matching with the time step of the values. That is what is done here. This is the important line. So simplified now. Score is simply a dot product of the query and the values. Decoder time step and the encoder outputs. Rest all of them are remaining same. The only thing which we have done here, I'll just show you, that you see the last dimension is always the vector, right? If you take the query with time access, your last dimension is the vector. So shape of value is also like this. But when you are doing the dot product, you will get 6 number of scores. They will look like this. You see, this is the score. These are the 6 number of scores which you will get as a result of this dot product. But that is coming as a last dimension. So this will not be helpful. We want a code to be applied for all the sequences. So which means that there are 6 sequence of values, and on those 6 number of times this 6 weights to be applied one by one, right? So that's how we change the shape here. Shape of the attention weight we are changing here, this place. Reshape it such that we shift it the weight here, so it becomes 161, which means 1 score for each of the sequence, 161. Now we are in a position to do the multiplication so that the weights are applied to these values, which is this 16512. So for each one of them, each of this vector is now multiplied by this weights. This is 6 number, this is also 6 number, and giving you the attention weights. One more thing you can note, that at the beginning, because it is not a learned layer, all the weights are almost same. You can see for 0.16, 0.16 and so on and so forth. All of them are almost same. And as the training progresses, the vector representation of the encoder's output as well as the decoder hidden state will change, and our network will be trained to maximize the score, right? That's how the score will be changing, and the similarity score will differ from word to word. So we have taken this attention layer just to demo only the one variety of the scoring mechanism. We are not talking about the local or global attention here, that we have not done here. Only the scoring mechanism, just to get a feel of how dot product is powerful to simplify this scoring mechanism. We also said that now it is not I-1 hidden state, but the ith hidden state that we'll be using, which essentially means that first we will feed the current word here. Decoder single input is passed to the LSTM layer, and then the output hidden state is now passed to our decoder attention train. You remember from that PPT. Rest all of them are same. The viewers who have not gone through my previous video, you can just go through one of the video, which is attention or RNN, where all these steps were described in detail. Let us have a look now how the training progressed. There is the improvement we can see. The training after 10 epoch has already achieved 96.87. You will recall that earlier this took around 20 epochs to achieve this kind of score, right? Primarily two reasons. Reason number one is the improvement we are making in the simplification in the network layer. Dot product is playing a role, and that in turn has allowed us to pump in more data, which we said that we have increased the data point to 40,000 from 20 to 30,000 to 40,000 this time. So together they have helped us to achieve better accuracy in lesser epoch. So if we could run more additional epochs, we could have possibly reached to 99% or so. Okay. Let's see how this time the attention is looking like. We have taken a word here. You see, this is the English word. I am a night owl. If you recall our last example, so the attention, we said that the attention, as long as these are diagonal, highlighted by light color, we know it is able to catch the meaning, the word-to-word correspondence in a better manner. So you can see that the shape is very diagonal, and you can just quickly check that here. Let's say I am this is ein. So exact match, right? It is beautifully figured out. And this is night owl, two words, but this is one single word. So it has caught it very nicely. Night owl is little bit shifted. Nevertheless, this is much better than what we have achieved last time. Let's go to other one, and you can see all of them is now following the diagonal pattern. Okay, and wherever you have dual meaning or multiple meaning of a single English word, there are multiple places were highlighted. Some more, see, more so. Let's summarize what we have learned so far. We learned that there are three broad categories using which attention was modified. The first one is the query sequencing step, were modified. Instead of using the I-1 hidden state as a query, we saw that the ith time step also can be used. We learned two concepts, local attention and the global attention. In local attention, we define a window size which can be either monotonic in nature, where there is an assumption of strong correspondence between ith decoder word and the ith encoder word. But this can be also predicted by a learned function, where the maximum weight is given in the mean position of the window, and the window is defined by a d distance, which is a hyperparameter for us. Next, we learned about three different ways of scoring. The scoring one is a dot product based scoring, which is much more simplified than the Badnau attention, where we had 4 neural network, but here without any neural network, just by simply doing the dot product between the words, we could get the similarity score. The second one was almost similar, only thing between the k and values we introduced a additional neural network to learn it. And the third one is akin to our Badnau attention, where concat was done between the query and key. Finally, we went through the code and observed that the attention plotting is much better than the previous ones. That's all in this video. See you in the next video.